Hi, my name is Weerathunge. I'm a PhD candidate in biomedical engineering at Boston University. My research advisor is Dr. Stepp. Today, I'll be presenting our work on developing a neurocomputational model providing laryngeal motor control for speech acquisition and production. We've named our model as LaDIVA to mean laryngeal diva model. So I first want to talk about the motivation behind our project. We know that articulatory movements are all labeled with much slower varying suprasegmental variations that convey important linguistic information beyond word meaning. Some of these suprasegmental features are vocal fundamental frequency and sound pressure level. Many behavioral studies have examined laryngeal motor control in both typical and atypical cohorts using these suprasegmental features, and they've interpreted laryngeal motor control in these populations using the computational framework of the DIVA model. But we know that DIVA model is optimized for articulatory motor control, so it's important to have a version of DIVA that is optimized and determines the laryngeal motor control. So to do that, we require a model of voice production integrating physiologically relevant models of vocalization and neurocomputational frameworks of laryngeal motor control. So this is the premise behind developing the LaDIVA model. LaDIVA model is a computational framework integrating two well-known computational platforms. The first is the DIVA model for neural control of speech, and the second is the extended body count model for modeling laryngeal physiology. We validated the model by comparing model performance with a behavioral paradigm dataset that we've collected before. And by these, we were able to replicate human vocal motor control and evaluate it both quantitatively and qualitatively using the model. The neural control of speech of LaDIVA model is controlled by the DIVA component of the model. DIVA in its core is a neurocomputational model. It's a set of mathematical equations which represents the connectivity between different brain regions. In a more granular level, DIVA is an artificial neural networks with nodes representing neurons and synaptic weights representing the connection strength between neurons. DIVA also has a control scheme with 3 different controllers. The first is a feed-forward controller that uses internally stored motor programs to generate sound signals. And there are 2 feedback controllers that detect and calculate the error between the desired output signal and the actual output produced. So there are several tuning parameters in DIVA model which can control the strength of these controllers. The first is the auditory feedback gain parameter, which controls the strength of the auditory feedback controller or auditory feedback controller. And we also have a very similar somatosensory feedback gain parameter, which controls the strength of the somatosensory feedback controller. And then we also have a feed-forward learning rate, which is a parameter which controls the strength of the feed-forward controller, or more specifically, the strength in which a persistent error is corrected and incorporated into the subsequent feed-forward signals in the model. Okay, so DIVA in its core converts motor commands into velocities of articulators. So we call this process as being done through a plant. The plant in DIVA is the vocal tract, so it converts motor commands related to the vocal tract to velocities of the articulators of the vocal tract. However, there's no plant that's inbuilt in DIVA model which converts laryngeal motor commands to velocities of laryngeal articulators. So that's what we were trying to achieve through LaDIVA. So we wanted to add a laryngeal plant into the system. So there were multiple selections or ways we could have done this because the physiology of vocal folds is modeled in high order finite element models to low order lumped element vocal fold models. What you see on the right is a 3-mass lumped element model developed by Ishizaka in 1972. So we used a very similar approach. We used the extended body count model, which controls subglottal and supraglottal features such as subglottal pressure and the intrinsic laryngeal muscle activations such as muscle activations of cricothyroid and thyroid muscles. Although extended body count model is computationally simple, it's complex enough to simulate and predict complex physical phenomena, both in typical and atypical voice production. So what you see here is the overview of the LaDIVA model. We've retained the control screen of the DIVA model, and we've retained the articulatory motor control capabilities of the DIVA model. And on top of that, we've added a laryngeal plant, which converts laryngeal motor commands to velocities of laryngeal articulators. So for this, the plant, we've added the extended body count model to LaDIVA to do that. So the laryngeal motor parameters of interest to us are activation levels of cricothyroid and thyroarytenoid muscles, and the acoustic signals, acoustic outcomes of this model are vocal fundamental frequency and sound pressure level at the laryngeal level. For the moment, we've kept the somatosensory feedback controller dormant due to two reasons. The first is because we wanted to check the acoustic outcomes of the system and compare it against auditory feedback paradigms. Altered auditory feedback paradigms. The second is that the somatosensory outcomes of the laryngeal motor control system is still being researched, so they're not as clearly defined as the acoustic outcomes. Due to these two reasons, we've kept the somatosensory feedback controller dormant at the moment. So our next step was to carry out a set of validations for the LaDIVA model. For this, we used a previous behavioral study with 20 adults with typical speech. This behavioral study contained two paradigms, a reflexive paradigm and an adaptive paradigm. So what we did was simulate the same paradigms through the LaDIVA model. So I'll first talk about the reflexive paradigm. Reflexive paradigms are generally used to characterize the auditory feedback control mechanisms in speech motor control. So sudden, unpredictable perturbations are applied to the auditory feedback of the participant, and the acoustic outcomes of the participant's response is recorded. So what you see in black is the group mean behavioral response for vocal fundamental frequency, and the error bars indicate 95% confidence interval. So we carried out a set of simulations where we replicated this reflexive paradigm in our model. And like I said before, we could use the auditory feedback gain parameter to control or change the strength of the auditory feedback controller. And based on that, we carried out a set of simulations. So the multicolored lines you see is the simulated acoustic outcome for different auditory feedback gain parameters. Similarly, we carried out a set of validations for the adaptive paradigm. So adaptive paradigms are generally used to characterize the strength of the feed-forward control of speech motor control. So sustained and predictable perturbations are applied for a sustained duration of time, and the ability of the speech motor control system to generate corrective commands and incorporate it to subsequent feed-forward commands is tested here. So like before, we see the behavioral response group mean value in black with the error bars, and we use the feed-forward learning rate parameter to change the strength of the feed-forward controller, and we generated a set of simulations through the LaDIVA model for adaptive paradigms as well. So now that we've carried out a set of validations using different altered auditory feedback paradigms, we also wanted to check another very important characteristic of motor control in LaDIVA model. And that's the ability to have the characteristic of motor equivalence. So motor equivalence can be broadly defined as the capacity to achieve the same motor task using different strategies. In the case of speech motor control or laryngeal motor control, we can equate it to achieving the same acoustic outcome of vocal fundamental frequency using different laryngeal muscle activation combinations. So we wanted to see, after adding the biomechanical components, if LaDIVA model retained the motor equivalence characteristics of DIVA model. So what you see here is a muscle activation map. For different combinations of CT and TA muscles, the output fundamental frequency is plotted here. So what you see here is essentially a set of isolines. So you can produce the same vocal fundamental frequency outcome for different combinations of CT and TA muscles. So essentially, motor equivalence is retained in LaDIVA model, but we didn't want to stop here. We wanted to go a step further. So we picked 4 different initial CTTA muscle activation combinations, and we ran a reflexive paradigm with this same parameters we wanted to have in the LaDIVA model for these different initial CTTA muscle activation combinations. What we found was interesting because we saw that the outputs of all 4 cases were very similar to the behavioral response that we got from the behavioral paradigm. And they fall within the error bar region of the behavioral data set. So it means that even though different initial CTTA muscle activation combinations are used, when presented with a reflexive paradigm, the model is able to produce the same required response or outcome in this case. One other interesting parameter we can check with the LaDIVA model is the muscle activation levels of the laryngeal musculature. This is very similar to looking at laryngeal electromyography signal, but as you know, in a behavioral setting, it is a very difficult signal to get because of the inaccessibility to laryngeal musculature. So this is very interesting for us to see, and we saw for 4 different conditions how the laryngeal muscle activations change when presented with the reflexive paradigm. So this is very interesting data set to us. So before I conclude my talk, I want to talk about one more simulation we did. This is regarding vocal fundamental frequency perturbations of running speech. So these kinds of perturbations look at how vocal motor control change in a more task-dependent manner. And in these conditions, the stimuli used are connected speech stimuli with different intonation patterns. So we basically wanted to see if an utterance of "Bye, Bobby, a puppy" can have 4 different intonation patterns, which could be used as stimuli for a running speech vocal fundamental frequency perturbation paradigms in future. So that's exactly what we did. So first I want to play how the phrase "Bye, Bobby, a puppy" would sound if none of the modifications of LaDIVA is added. So in a basic DIVA model, this is how "Bye, Bobby, a puppy" would sound like. Bye, Bobby, a puppy. So it's very monotonic, no intonation incorporated. So next we asked one of our co-authors, Dr. Frank Guenther, to record 2 of these different intonation patterns for the utterance "Bye, Bobby, a puppy." So I'm going to play the utterances that he made first as a statement and then as a question.
Bye, Bobby, a puppy. Bye, Bobby, a puppy.
Okay, so then what we did was we extracted the intonation patterns and used those intonation patterns for the 4 different intonation patterns as vocal fundamental frequency targets. So what you see on the right are the 4 different intonation patterns extracted as vocal fundamental frequency contours. And then we fed it to LaDIVA model as vocal fundamental frequency targets and observed how the model tuned those acoustic outcomes through the acoustic synthesizer. So this is what the model output sounds like for the same sentence and question that I played earlier. Bye, Bobby, a puppy. Bye, Bobby, a puppy. So you hear a clear difference in the intonation patterns in these cases. So with that, I'd like to conclude this talk. We were able to successfully incorporate laryngeal function to DIVA model using the LaDIVA model. We've carried out model validations by comparing reflexive and adaptive behavioral responses with model simulations. We were also able to observe mode equivalence in the combined system, and we were also able to simulate different intonation patterns for connected speech stimuli. We believe that LaDIVA will be a powerful tool in advancing understanding of typical and atypical voice production in future. So with that, I'm going to acknowledge our collaborators, Drs. Zañartu and Dr. Frank Guenther, and of course the Stepp Lab and our funding sources. If you have any questions, suggestions, and comments, please feel free to contact me at my email address and all my contact details that's provided here. Thank you for listening to my talk.